Swayam Prabha. Digital India. Educated India.
Hello and welcome to another lecture on control systems. So in continuation with what we were doing in the previous lecture, where we saw that apart from these two earlier sort of preliminary realizations or realization methods of state space systems, state space realizations that we saw from transfer functions, yeah, there was also this sort of a diagonalization or diagonal form of the system matrices, that A matrix turned out to be diagonal when you had distinct poles that were real, yeah. Then we saw that if the transfer function's poles were real but not distinct, then that hope of having the diagonal realization is almost dashed, actually dashed, not almost, it's dashed. In that case, what is the best thing we can do? We saw that we can then sort of combine this parallel and cascade combo together and still get as close as possible to a diagonal form, not exactly diagonal but in the so called Jordan form, yeah. So don't worry about how you get to that Jordan form, how to derive all that, we will probably get to that, we will not get into the great details because that requires a lot of proof and some advanced linear algebra, but we will just maybe if possible outline the method for getting the Jordan block and then take an example or so, but in general we shall not bother ourselves with that. We will only need that when we try to solve this state space equations, which is what we intend to do in this lecture at some point. Anyway, but even before that, we have this burning question still unanswered. We have still not considered the possibility of complex poles, and it turns out that if you have complex poles, you cannot factor them out into linear factors. So you cannot factor out a pair of complex conjugate poles, say P1 and P1 star, right, into S plus P1 and S plus P1 star, two linear factors, and then realize it, because for realization you only have real numbers or physical quantities which are all denoted in by real numbers, not by complex numbers. So then what do? You have to remember this realization, the word real is very much there in the word realization, like state space realization. We cannot leave something on in the complex domain and say, yeah, I have given you a transfer function, I have given you linear factors. Well, for solution purposes that is fine, but if you are trying to simulate this on an analog computer, then you better come up with a realization that involves real quantities, real variables, not these complex quantities, right, because you cannot realize them. So then just to recap what we did, we saw that in the last lecture that if you have repeated but real poles, this is probably the best you can do, yeah, where this particular form is what we call the Jordan canonical form for that repeated pole structure, and the remaining ones which were simple poles, they gave us the diagonal form nice and clean, right. So this is not exactly diagonal but still reasonably satisfactory for our purpose. But now suppose you land up in a situation where you have this alpha s plus beta upon s squared. So I am absorbing, so even if this denominator is not a monic polynomial, I can absorb it in alpha, yeah. So I generally get this monic polynomial s squared plus 2 zeta omega n s plus omega n squared, yeah, with omega n greater than 0 and zeta between 0 and 1. We have seen this countless number of times when studying these topics related to classical control, particularly transient responses. So obviously then the poles of this GS are complex. Yeah, there is a complex pair of complex poles, complex conjugates of one another. Yeah. Now how do you realize this sort of a system? So of course you can do something here. What you can immediately do here is method of completing squares. So if the poles are like S is equal to say A plus JB and A minus JB, then you can write this denominator as S minus A whole squared plus B squared. Yeah, that I can do, because I know that if the roots of this polynomial equation, that is if I solve S square plus 2 zeta omega n S plus omega n squared is equal to 0, then these are my roots, right. And if I solve this polynomial, then also these are my roots. So this polynomial can then therefore be written in this form. Yeah, it is one and the same, just completing squares. But what is the benefit of this? So let me just go one step further, and S minus A plus alpha A plus beta upon S minus A whole squared plus B squared. So then I get to the stage where I divide both numerator and denominator by S minus A squared, and here is what I am going to get. So I am going to split it up into two terms. So this is what I get, S minus A upon 1 plus B squared upon S minus A whole squared plus beta plus A alpha, yeah, divided by S minus A whole squared upon 1 plus B squared upon S minus A whole squared. But why is this intriguing, you might ask? Yeah, notice now that we have done all the classical control topics, this reminds us of something, doesn't it? Doesn't this remind us of a feedback structure that looks something like this? So suppose I have alpha by, or rather let me pull out the alpha. Yeah. So let us say I just have the alpha somewhere outside here. So in the forward path, if I have a transfer function by 1 by S minus A, and in the feedback path, suppose I have another transfer function which is basically 1 by, or rather B squared by S minus A. What does that give me? Yeah. So I put it to you that you check, this is a trivial exercise now. Having done so much of classical control, this is a trivial exercise now. If this is your u and this is your y, then you check that the transfer function between this u and this y is given exactly by this term. Yeah, this transfer function is given, this blue part is realized exactly by this. Yeah. What is the benefit of all of this? Well, it will be clear in a moment. For now, let us try to understand this and focus a bit and convince ourselves that this is indeed so. You see, we have already seen that the forward and the reverse path, we've already seen block diagram reduction techniques, right, in classical control. So this is the forward path transfer function, this is the feedback path transfer function. So you have the G forward divided by 1 plus G forward into G feedback. So therefore this divided by 1 plus this times this, yeah, and then you just have the alpha outside. So this is indeed, I am convinced that this blue part, that blue box I have put it in, this is indeed a realization of this blue box. But now you might be a little worried at this point, thinking, well, I was trying to realize a second degree differential equation or a second order transfer function, right, with two poles. I have already used up two of these poles, so these are like basically two integrators. Yeah. So in order to realize the second part, I should not be using another integrator, right, because if it is a second degree differential equation, then I should be able to realize it just using 2 integrators, but the 2 integrators are already sitting here, no. Of course this is 1 by s minus a, but I know that 1 by s minus a is nothing but just this a here, no, yeah. So this is basically, I have already used up 2 integrators here, one in the forward path, one in the feedback path. So in order to realize this, I should be able to do that without relying on adding more integrators, yeah, I already have enough integrators. So how am I going to do that? So well, here is how we can do that, okay. Now you see, what if I took this u here, yeah, and I okay, so I took this u here, let us say, and instead of taking the output from here, if I took the output from here, what if I took the output from here, what would be my output from here? So let me open that up a little, let me not draw it in a congested manner here, let me just use an entire slide for this because this requires a little bit of thought. So this is 1 by s minus a, whenever I am drawing this 1 by s minus a, at the back of your mind you should view this as an integrator like this, and then some gain like this, then a summer like this, yeah. So this is basically your 1 by s minus a realization, okay. So essentially when I am doing this 1 by s minus a, at the back of your mind you should always imagine that an integrator is being used up for realization of such a factor as this, okay. So let me redraw that back again here, yeah. So what I had was, I said that, well, let me have this y here, let me have this here, let me have the alpha here, this is the u here, the u, the big U, okay, and let me have this and this b squared upon s minus a. So again this is a realization like this, only thing that there will be a b squared sitting somewhere over here, or somewhere over here, whether you like it at the input side or the output side, it is up to you. So then, then this I am claiming, and I have shown you also convincingly, that this is nothing but the realization of this blue fellow here, right. So this blue fellow is already realized. What about the second fellow here? What about its gain? See here I am passing it through a gain alpha, right. So if I am passing this through alpha, then at the output, yeah, I better divide it out by something else in order to nullify the effect of this alpha, because what is going into this system is alpha u, but what is going into the second system is beta plus a alpha times u, is it not? So I must adjust this at the output somehow, but even before that, where do I get this output? So I am claiming, or I am suggesting, that why don't we take a tapping point at this and take this as our output 2. So let us say this is y1 and let us say this is y2. So what is this y2 here? Now notice, if I now were to redraw this, this would entail that I am as if, so this is because a linear system, its superposition is valid here. So let me ignore this y1 for the time being and let me just consider this y2. So what is the forward path transfer function? It is 1 by s minus a whole squared into b squared, yeah. So this is the forward path transfer function. What is the feedback path transfer function? It is just unity, because see this is where the output is coming out for y2. So in the post the output, what is there in the feedback loop? Just unity, yeah. So then this, for viewing from this point here, from this u tilde here, if I look at this y2, what is the transfer function? y2 upon u tilde. This is going to be nothing but b squared by s minus a whole squared upon 1 plus b squared upon s minus a whole squared. But this is not a big deal, no, this is not a big problem for me. right, because now I am almost there. Look at this term. What is differing between this term and the term I have got here? See, the denominator is the same, denominator I have realized, only thing is the gain of the numerator, but that I can always adjust. I can just put a block here which is going to divide by b squared, I am going to multiply by this beta plus a alpha, and I am done, beta plus a alpha, and I am done. So instead of calling that earlier fellow as y2, now if I call this fellow as my y2, then I better sum them together, yeah. So this is going to be my y1 plus y2, and that is a realization, right. But why you think is this realization beneficial? Well, let us go one step deeper into this. So suppose you have this here alpha, yeah, this summer here, and now as we do in state space realizations, we are going to just look at the bare essentials, those integrators and their so called outputs, yeah. So this is going to be this a here, I hope there is no mistake there, right, and then we have this tapped out from here, we have another channel that is going on here, okay. So I can readily already define this as x1 and this one as x1 dot, okay. And what about this channel going on here? So let me put a b squared here, yeah, that is a b squared over there. Then I can put another sort of integrator here, of course in the reverse direction. So this time this is going to be the output of the integrator, so this is going to be x2 and this is going to be x2 dot. What is going to be fed back in is again that same thing, gain a, yeah. So this is basically b squared upon s minus a, yeah. So this goes here in this channel, right, okay. And then I am saying that this channel out here, whatever is the output, I am just tapping it out here, passing it through this gain, this beta plus alpha a upon b squared, and calling this as my output. So then I wonder what sort of a state space realization this will lead to, okay. So let us write down quickly what this basically entails. So what is coming in here at x1 dot? So I can write x1 dot is going to be equal to a x1 as this channel suggests plus, well, you notice that this is actually a negative feedback, right. That is the reason why we have this positive sign in this denominator, right. So if this is a negative feedback, then it is actually minus x2 that is going in through this channel, right. So therefore it is going to be minus x2 and of course plus alpha times u, right. I can also omit the t argument, it is meaningless because I am not maintaining that throughout. So it is alpha u, right. So that is x1 dot. And what about x2 dot? Now if I write the equation for x2 dot, then I observe that this is going to be again, you see this a times x2 plus b squared times x1, and that is it, no external input. So it is a times x2 plus b squared times x1, yeah. So okay, let us also complete the story by writing the output equation. What is the output equation? Output equation is, well, you see it is just x1 coming through here, but here x2 gets multiplied by this factor, that is beta plus alpha a upon b squared, right. So therefore it is going to be x1 plus beta plus alpha a upon b squared times x2. Now if I write this in a compact form, so I am going to squeeze out a little bit of space for myself here and I am going to write that in compact notation, and you will get this. So x dot is basically x1 dot and x2 dot written in the form of a vector, then you will see that this A matrix turns out to be A minus 1 B squared A times X plus, of course there is just this alpha here and 0 here, times U, and Y is going to be this 1 and beta plus alpha A upon B squared times X, yeah. So this is going to be my C matrix, this is going to be my A matrix, this is going to be my B matrix. Now conventionally, if you look through standard textbooks, you will see that this often takes the form of A matrix that looks like A minus B, B, A, and you might wonder what is the connection between these two. Well, in order to understand that, just notice that I have put in this, this block B squared here, right. So if for instance, instead of putting this B squared here, you had split this up and you had put this B here and you had placed another B here, yeah. In that case, you see how would this equation have changed, in the sense that in the first case then it would, instead of getting this x2 right up, you would have gotten minus B times x2 here. So then there would have been a B here, and instead of getting a B squared here, the squared would have vanished, because then you would have had this x1 times B. But after all, when you put, whether you put this B squared followed by a different block, or you put B followed by that block and then B, these are equivalent systems, yeah. We know by block diagram reduction techniques that these are equivalent systems, right. So it is one and the same. So this matrix, I put it to you, and this, they represent the same system, it is just that the interconnection how I have viewed it. But the bigger picture and the bigger story to take home from this is that, look, when we have complex poles or complex eigenvalues, okay, we haven't even talked about it yet, what these eigenvalues are and what their connections to poles are. We will do that shortly, maybe in a lecture or two, but for the time being, if you permit me to look at this transfer function and at least comment that this transfer function has complex poles. Now, if you have complex poles, you cannot clearly split it up into first order factors such that, you know, it is just 1 by s minus p1 and 1 by s minus p2, where p1 and p2 are poles, quite simply because p1 and p2 are complex numbers and I have no way of realizing complex variables using the physically realizable circuit elements. But now, with this sort of a massaging of this system, I have actually obtained a realization using just first order blocks, where of course each individual block does not per se talk about the poles themselves, but if you notice carefully and squint your eyes and see that this actually talks about the real part of the pole, right. So in a very clever way, we have sort of partitioned this in a way, we have split this system up in a way, we opened it up such that it can still be realized by first order blocks, that is the integrator and a feedback structure with it, yeah, and all the quantities, every gain and every element that you see here is physically realizable using circuit elements, because they are all real numbers after all. That is the biggest take home from this. So what is the compromise, you might wonder? Well, the compromise quite simply is that you cannot get this pure diagonal form, right. Just like when you have repeated real poles, you will not be able to get this diagonal form, but rather this so called Jordan chain, again something that I have not discussed, probably we will discuss in a later lecture, but you will get these Jordan blocks, yeah. So it is close to a diagonal block, but it is not quite there yet, yeah. That is what we saw with repeated poles. Now with complex poles also, we see that you cannot realize them in this pure diagonal form. So the best you can do is get this 2 by 2 block to sit in the diagonal, yeah. So this 2 by 2 block basically is a proxy for that diagonal 1 by 1, where you have 1 by s minus p1 and 1 by s minus p2, yeah, sitting on the two diagonals, or rather s minus p1 and s minus p2 sitting on the two diagonals, right. So instead of being able to do that, now we have to do this compromise, but the good thing is that it is no bigger than a size 2 by 2. So although it is not a diagonal matrix, it is after all a 2 by 2 matrix, and we are pretty comfortable handling 2 by 2 systems. So I put it to you that this is actually an advancement of sorts, yeah. So I hope that you appreciate that we have now covered 3 ways of realizing. We will give them proper names later on. This is of course known as the diagonal form realization, or the quasi diagonal form realization, or whatever you call it, because it is not really strictly always a diagonal form. If it is not diagonalizable, there is no way you are going to get a diagonal form, right. So that is one of the things we have seen. The other 2 forms we have seen are the phase variable form and the, the first form where we saw how we build the circuit up from op amps, yeah. So we have seen 3 forms. Of course there are several other forms which you can look up in standard advanced level textbooks and you will find, but we will not really get into too many of those forms, yeah, without really understanding what those forms entail or why people came up with those forms. So maybe later on if we have time and if we are able to cover that part, the relevant parts, then we will get into the story behind why each of these forms is important in its own right, okay. Before we kind of close this discussion about modeling and state space realization and stuff, and the next topic is going to be like trying to solve the system of equations, the state space system of equations. Before we do that, just to give you a glimpse into some different kind of a system, not necessarily an electrical system. For electrical systems it turned out that we have an intuitive understanding of the system, so to determine how many states are there, what the size, what the differential equations are like, it's relatively easy. But now suppose you have a mechanical system like this, again this we have covered quite adequately in the modeling part when we did initially. But let us say you have this kind of a setup where you have this M1 and this is, let us say, D, and then you have a spring with spring constant K, and then you have M2, yeah, and suppose there is a force F that is being applied here, right. So then how do we write this equation? Well, of course this you call as the position of the first particle or the first mass, and this you call as the reference point and the position of the second mass P, yeah. So we have P1 and P1 dot and P2 and P2 dot, which will appear in our dynamics. How so? Let us see. So if you draw the free body diagram and analyze, I am not going to do this because we have done this so often now. So you convince yourself that it is indeed so. We are going to write F, the applied force, and we are going to write this from the free body diagram of M2. So what is going to be M2? Remember what is the force on M2 that is going to be balanced. So M2 P2 double dot, that is the pseudo force that is being balanced, yeah, to put it in static equilibrium, plus this K times, what is going to be this? Well, this is going to be x1 minus x, sorry, I have called it P here, right, because x I have reserved for the state variables, so I have to be careful now. So this is P1 minus, sorry, P2 minus P1, yeah, okay, I have probably labeled it incorrectly, yeah, now it is correct. So P2 with M2, P1 with M1, okay. So this is my first equation, and what about my second equation? Well, the second equation says that again this M1 P1 double dot is going to balance it out, and it's so this is being for this D is going to be D P1 dot plus what is this? This is K times P1 minus P2, and there is no externally applied force per se, so it is going to be 0. So this is second. So now you have two equations, two differential equations, and the first question you must ask yourself is, what is going to be the size of the state vector? How many states are there? Yeah, and yeah, when you have a single differential equation, you can generally look at the degree of the differential equation and infer that that many states are required. But now you have two differential equations, of course they are coupled. So if you want, you can actually sort of write this as a single differential equation, maybe by differentiating suitable variables repeatedly, yeah. So maybe you can differentiate this P1 one more time to get P1 dot and P2 dot in this expression, and then differentiate this once more, that is P1 4 dot, yeah, and then this P1 double dot, triple dot, and then this P1 get derivatives thereafter, and then get P2 double dot and then substitute it from the first equation. But it is reasonable to not do that and instead observe the system of equations and conclude that, look, the first equation involves a second order or second degree differential equation. Yeah. So it will require two states. The two states will be this P2 and P2 dot, and similarly these are from the first equation, and the second equation also involves just P1 and P1 dot, the new variables being introduced here, right. So if you just have P1, P1 dot, P2, P2 dot, you can write down both these equations, right. So without sort of messing around too much or trying to write this as a single ODE and seeing what the degree of that ODE would be, yeah, we would rather like to kind of be able to determine the number of states or the size of the state vector just from our physical understanding, and the physical understanding tells us that we need 4 states, yeah, so 2 from the first equation, 2 from the second equation, right. So how do we go about this defining these 4 states? So let me define P1 is equal to x1, P1 dot is equal to x2, P2 is equal to x3, and P2 dot is equal to x3, x4, yeah. So define like this, so define the states in this fashion, okay. So again, of course we can do this because we have an understanding of the system, we have spent so much time on modeling mechanical systems. So if you get a rotational mechanical system, even with gears and all, if you get an electromechanical system, which are systems we have seen, yeah, you should be readily able to get to their state space realizations, okay, and be able to immediately determine how many states will be there, what the state vector will be like, and what the matrices A, B, C, D, those state space realization matrices A, B, C, D will look like in such a case, right. Okay, so then from this equation what do we have? X1 dot is equal to P1 dot is equal to x2, that is my first equation. What about x2 dot? X2 dot is equal to P1 double dot, and I wonder which equation is going to tell me what P1 double dot is. Of course it's the second equation, yeah. So that is basically going to be d by m with a minus sign P1 dot, which is x2, yeah, this P1 dot, remember this is now my x2 by this definition, and plus k by m, of course with a minus sign, sorry, not plus, yeah. So with a minus sign, minus k by m P1, what is my P1? P1 is nothing but x1, and then with a plus sign, because remember I am pushing every other term other than the MP1 double dot, I am pushing all of this term on the other side of the equality, so therefore they will carry a negative sign. So this kp2 will carry a plus sign, so it will be k by m, and what is p2? P2 is x3, yeah. So I have the second equation. What about x3 dot? Simple, x3 dot is again very simple to evaluate, x3 dot is nothing but p2 dot, which is x4. So here I have my, it is kind of similar to the phase variable but not quite, because we have two different equations here, we are not writing this as a single equation, okay. So it is kind of reminiscent of the phase variable form, but not exactly, not quite, yeah, because there is a coupling between two different systems here through the spring, so that is what is messing up the so called phase variable structure here. So that is why you see this is not just a 2 by 2 system, this x1 involves only x2, x2 involves x1, x2, but also x3, the x3 is coming into the picture because of this coupling in the means, by the means of this spring here. So then the final equation, which is x4 dot, which is nothing but p2 double dot. What is p2 double dot? I can use the second equation now here. So if I use the second equation here, then I get, of course the first thing is 1 by m2, so let me write this as m1, I have missed the subscript. So this is 1 by m2, f is obviously going to be there, this is the force, this is the external input, yeah, What about the other terms? Minus k by m2 p2, minus k by m2 p2. What is p2? p2 is x3, yeah, plus k by m2 p1, p1 is x1, yeah. So this is my fourth equation. So if I now write this up in the matrix notation, what's it going to look like? So x1 dot, x2 dot, x3 dot, x4 dot is going to look something like, let's see, what is x1 dot? It is going to be just x2. So I can fill up this matrix as 0, 1, 0, 0. Yeah, this is x1, x2, x3, x4, and let me also keep the B matrix free here. So of course nothing appears in the B matrix, so the first is 0. The second column, x2 dot. So what is x2 dot? The second equation, I have minus k by m1 appearing in the first column, yeah, then minus d by m1 appearing in the second column, and a plus k by m1 appearing in the third column. So let me repeat, minus k by m1 minus d by m1, so minus k by m1 minus d by m1, and I believe a plus k by m1, so k by m1 and a 0. What about the third? x3 dot is nothing but, and of course there is no force, so let me fill out the B corresponding B vector as well. So the second equation you see has no F or externally applied force, so this is also going to be 0. The third, x3 dot is equal to x4, the third equation, right. So that is 0, 0, 0, 1, 0, 0, 0, 1, because this is going to filter out just this x4 from this vector. And of course force, the externally applied force does not make any appearance in this equation either, so it is going to be 0. What about x4 dot? Well, x4 dot is where the force appears, so it is 1 by m2. So I must have this 1 by m2. What about the coefficient of x1, x2, x3, x4 in this equation? Well, just look, you have x1 appearing with k by m2. Yeah, I believe was there a minus sign missing here? Let's see. So I have k by m1 p2, p2 is x3, so that is going to be with a minus sign, yeah, and x1. So x1 is going to be just this, this p1, right, so that is going to appear with a plus sign, yeah. So it is k by m1, k by m2 0 minus k by m2 0, so it is going to be k by m2 0 minus k by m2 and 0, yeah, that's what the structure is going to look like, okay. So this is my x dot is equal to ax plus bu form, yeah. What is my y going to look like? So y, I can choose whichever y I am interested in. So suppose I am interested in p1, yeah, in that case my y will look like 1, 0, 0, 0. x1, x2, x3, x4, yeah. So that is my representation. So even if I am given a mechanical system, you see, by writing out this differential equation, these differential equations from the free body diagrams, yeah, I can still get this this representation, yeah, in the state space form of the standard type x dot is equal to ax plus bu, y is equal to cx, yeah. So that kind of brings us to the culmination of this foray that we had into state space representation of systems from ODE, from a given ODE. We have also seen how we can go back to the transfer function from the state space domain. Of course, we are not going to try and do that with this 4x4 system here, it is going to be too laborious. You can try it out with some numerical values and check what sort of a transfer function you get, okay. So that I leave that to you as an exercise choose some appropriate numerical values for k, m1, m2 and d, and obtain the transfer function from u to y, that is from the force, applied force to y, okay. So once you do that, just check that the classical model that you had earlier obtained, yeah, that they agree. It's a very ready-made check for you, right? You've already seen how you can do that. So instead of just now taking the Laplace transform of these individual equations one at a time and then eliminating variables and obtaining the transfer function, why not just go into this model based approach, yeah, this state space representation, and take Si minus A inverse, yeah, and pre-multiply it with C, post-multiply it with B, yeah, and you have the transfer function, yeah. So you verify by both methods that indeed it agrees. You already know how to model this in the transfer function domain, so get that transfer function from the transfer function domain, use some numerical values, and then just for practice do the same thing with this state space realization and just use the expression C into Si minus A inverse B and see that the two transfer functions agree, yeah. So then you know that this model is correct irrespective of whether it is in the transfer function domain or in the state space domain, and that you have not made any careless mistakes, as I am quite accustomed to doing pretty often, which by now you might have already seen countless times. Anyway, so with this we are now at in a good position to go into the next or begin the next part of our journey, yeah. So let me draw a line here. So next we are going to try and see the solution of the state space equations, and the first solution that I am going to suggest may not be very satisfactory to you, so I might warn you beforehand, yeah. See, we know how to solve this in the transfer function domain, but clearly there are some inadequacies of the transfer function domain, which is why we went into the state space. One of them chiefly was this inability to capture the internal descriptions that we have seen, right. So we do not account for these initial conditions, the non-zero initial conditions, when we just look at a transfer function, and thereby we might miss out on some important property of the system, yeah, something as important as the stability itself, right. So that is why we went into state space. But now if in trying to solve the state space equations you have to eventually resort to transfer functions, you might not feel very satisfied, because you say okay, you came up with a new method, but it seems you still have to go back to the transfer function domain. So why not let me be a little more careful in the transfer function domain itself and account for those initial conditions at the differential equation stage. Let me not go into the transfer function, let me just take the differential equation as it is, start with the differential equation, very carefully plug in all the initial conditions and study the response. You could do that, but I promise you that after seeing the first method of solving this state space equation, we will indeed present to you a method whereby you can completely bypass the use of Laplace transforms, okay. Because as long as you are using Laplace transforms, you will invariably get the feeling that this is after all old wine in new bottle, yeah. We are selling this to you as some new method, this transfer, this state space method, this modeling and all this, and we are giving you these fancy terms and all of these things, right. But if at the end of the day you are still using Laplace transform, yeah, then basically you have not cut the umbilical cord from the parent method that you had learned like towards the beginning of this course, right. So you wonder that isn't there a way to completely give up or completely forsake this Laplace transform method and still be able to solve the state space equations, yeah. So I want you to keep that question ignited in your mind, yeah. But for now the answer I am going to give you, or the method that I am going to outline, is not going to be completely satisfactory from that perspective, because we are still at the end of the day going to use this this so called Laplace transform. How? Well, here is how. So look at this equation here. You have x dot is equal to ax plus bu and y is equal to cx plus du. As you might recall, you see what we did here was we took the Laplace transform. So this is my state equation and this is generally called the output equation, okay. So I take the Laplace transform of this, yeah, minus x naught minus, yeah, that's standard Laplace transform, nothing fancy about this, yeah. It's basically n first degree differential equations. So I have the Laplace transforms of their derivatives, yeah. I'm just writing s x1 s minus x1 0 minus s x2 s minus x2 0 minus, so on till s xn s minus xn 0 minus. That's all that I'm doing, that's what this vector is, yeah. So this term, this entire term is nothing but this, just an efficient way of writing it. And then I write on this side, of course the a is going to be a constant, so this is going to be xs plus b is again going to be a constant, this is going to be us. So again I go back to this si minus a, I gather together all terms related to xs, yeah, and on the other side I push this x0 minus plus b us. The interesting thing that you might now notice is that this representation, this particular equation makes that idea of 0 input and 0 state response very transparent, yeah. Now you see, earlier when we told you about the 0 input and 0 state, we hadn't even defined what a state was, we've just asked you to take it on faith and push with it. Now you begin to see why those two are called 0 input and 0 state. Suppose x0 minus is equal to 0, yeah, implies xs is equal to nothing but si minus a inverse b times us, yeah, and this is indeed what we have been terming as the 0 state response. On the other hand, suppose us is equal to 0, so you are not applying any input. This implies that xs is going to be nothing but si minus a inverse times this x0 minus. This is what we have been terming as the 0 input response, okay. So now you see that those two are clearly and transparently partitioned out from the total solution, okay. So now by superposition you can treat these two as two different components that are going into the making of this response, into the building of this response, okay. So by superposition we can take them acting one at a time and then sum together their results, right. So we can have, let us say, let me put a subscript here, so this is xzs and this is xzi, yeah. So then we have that xs overall is equal to xzss plus xzis, which is the 0 state response and the 0 input response. And once we have solved for x, if we have, that is, then it is trivial to just find out what y is going to be, because y is nothing but well, let me not leave that out. So y is going to be nothing but this c times xs, yeah. Remember, this is a vector, this is also a vector, yeah, but each term in that vector is a function of s because it is a Laplace variable, Laplace domain variable, yeah, right. So it turns out then that the only key to obtaining the solution or obtaining what y is going to be in the time domain is, once we have solved for x, we are done. But then are we there yet? Have we actually solved for x yet? Let us just focus on these terms one by one. Let us first focus on the 0 input response. So focus on x 0 input of S. Yeah, that is going to be this Si minus A inverse x0 minus. Yeah. And now you wonder, okay, all that is fine, but you know, if we want to find out the time domain version of this, the 0 input, then I better take Laplace inverse of this whole thing Si minus A inverse x0 minus. Now of course I can take the x0 minus out because it is just a constant, so this is going to be nothing but Si minus A inverse and then this x0 minus. Yeah. So then the key step or the key to all of this is if I can somehow manage to obtain this, yeah, then I would have solved at least the 0 input part of the state. Yeah. So how am I going to do that? And this is the reason why I said it may not be very satisfactory, because after all you see already in going from the state space to the transfer function domain, I have shown you how we can obtain this for any given A matrix, how we can obtain this Si minus A inverse. Of course you know how to take matrix inverses, that is nothing I have taught you new in this course. The only thing is that now this matrix inverse, each entry of the matrix inverse is potentially a function of this complex variable S. And now what you have to do is, well, you know that what each entry of this Si minus A is going to look like, Si minus A inverse is going to look like. I have argued to you why each entry of this Si minus A inverse cannot be anything but a strictly proper, yeah, can be nothing but a strictly proper rational function. Yeah. So I have established that much at least to you, that this is going to be a strictly proper rational function. So if it is a strictly proper rational function, then each individual entry in that Si minus A inverse matrix, which is n cross n, you can take the Laplace transform, I mean the Laplace inverse, and get the time domain representation. Yeah. So that seems like, you know, not very efficient really. So what do we do with this? Can we somehow do something better with this? So that is what we are going to see, and that is probably the last thing we are going to see in this lecture today, and then we are going to continue with this, looking at the solution of this system of state space equations in the next lecture. So now consider this thing, consider this Si minus A inverse, okay, and let us say that I take this S out of here and I minus A by S inverse, right. S is just a scalar, so that is going to be nothing but 1 by S times I minus A by S inverse. So now at this point I am going to make a claim which you may, the more mathematically inclined among you might find a little troublesome, yeah, a little difficult to sort of reconcile with. Yeah. What I am going to say is that, look, this is a matrix, I agree that this is a matrix, yeah, but think of the expansion of the series 1 minus, let us say, what do you call it, 1 minus beta inverse. Yeah, we know that when beta is smaller than 1 in magnitude, so if beta is smaller than 1 in magnitude, yeah, then we can expand this in the following fashion. Yeah, this is basically that GP series that you have learnt about, right, the geometric progression, the infinite geometric progression, yeah, right, likewise. So this is basically an infinite series, right. So what I am going to now claim is that we are capable of doing something similar, we are allowed to do something similar with this series as well. Yeah, only that instead of this beta being a scalar here, now we have a matrix. Yeah. So of course I understand that you might find it a little difficult to believe me that this series can be done, this series can be expanded like this. we will show you alternate ways, and we will have alternate ways of convincing you that this does work, but for now at least you should please carry on with this in this journey with me and believe for now that this can be expanded in this series. And in that case we have this I plus a by s plus a squared by s squared plus so on. Now if that is so, then how about the Laplace inverse of this Si minus A inverse? If we can actually expand this in this series, now you see I have to do nothing but take the Laplace inverse of this apparently infinite series. So this is I 1 by s times I plus 1 by s squared times A plus 1 by s to the 3 times A squared plus, in general the term looks like A to the power r multiplied by 1 by s to the r plus 1 plus dot dot dot, an infinite series. But now because of the linearity property of the Laplace transform, I can take the individual Laplace inverses of these. So then I would be allowed to write this as, notice if I take the Laplace inverse of this, I can just leave these constant matrices I, A squared as they are and just pass this operator through this 1 by s squared. So then what I will have is I plus At plus a squared t squared by factorial 2 plus dot dot dot, and here you have this a to the r t to the r by factorial r, that is a general term of the series, and it goes on till infinity. If that is so, then I can say that, well, my x0 input, sorry not this, the small one, the time domain version. So x0 input t is going to be nothing but this I plus At plus a squared t squared plus dot 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 by factorial 2 plus dot 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 like this times x naught, or rather let me see this, yeah, so this x0 minus, yeah, so that can be my expression, right. So now instead of calling this series, remember we have this exponential series for the scalars where we had x e to the x is equal to 1 plus x squared by factorial 2 plus so on, but this was obviously derivable. Here on the other hand we define this as a matrix exponential. So remember this is a key important point, yeah, if someone asks you derive that e to the at is given by this series, there is no such derivation that exists. So you can think of this e to the at like a placeholder, because it has such a similarity with the corresponding scalar exponential, that is why we call it e to the at, but in reality it is this series, yeah, this is just a placeholder, just a symbol that stands for it, there is nothing to derive in this, okay, this is just a definition that we are giving, and the definition is that this e to the at is given by I plus at plus a squared t squared by factorial 2 plus so on, that infinite series that we have here, okay. So therefore in compact notation, once we have denoted the series by this placeholder, if you permit me, we can write that x zi t is given by e to the at times, so this obviously is going to be a matrix e to the at times x0 minus, okay. The way to evaluate this e to the at is still, yeah, this is just a elegant sort of a notation that looks pretty, but let me summarize, and with that we will end today's lecture. Let me summarize, I have not given you any magic formula to evaluate the zero input, yeah, that can like readily tell you, I have not given you any additional method to what you already know. In other words, if you are given a system of state space representation of a system, say A, B, C, D matrices, and if you are asked to find out the zero input response of the system, then what you have to do is you have to take this Si minus A inverse matrix, right, look at each individual entry of that matrix, take their corresponding Laplace inverses, and you will get some time domain functions. Of course, those time domain functions will look like exponentials only, yeah, exponentials and sinusoids and cosinusoids like we are so familiar with now, because those are rational functions. We know what sort of inverse Laplace transforms rational functions throw up, right. So those will be maybe some polynomials, exponentials, yeah, that is all that we can get out of this, right. So by means of all of this that we have done so far is just that we have come up with this representation, this is how it looks like, right. I have not given you any method. So far what we have seen, yes, there is a way to solve the state space equation, but eventually you have to still rely on that Laplace transform, okay. The Laplace transform is still on the Mickey on your back, okay. So in the next lecture we shall take up some examples and we shall see how you can get this Laplace inverse of this Si minus A inverse. Already we have seen some of those transfer functions, how they look like, yeah. So now if you want to evaluate that, it will be pretty laborious. Even for a 3 by 3 system you have to carry out 9 inverse Laplace transforms, right, pretty laborious. So we want to actually cut that process short, so we will learn a couple more techniques in order to do that, okay. So till then, take very good care, thank you.